There's only 12 sessions coming up anyway.
Right, gents. Engineering, Science, Electrical. So you've already had a session with Omar this morning. Your Omar session will normally be here. Yep. Okay. Not in this room, but in this slot. So me 3 times, and then Omar is you. Alright. So I'm covering Learn and Outcome 2. Investigate and apply direct current, DC, and alternating current, AC theory to electrical circuits. The assessment of this, 50% of the overall assessment, the other 50% is OMAR. And for electrical, you've got to do 1 practical investigation and lab report, okay, and you've got to do an examination of 1 hour duration. Yep. You have to pass a minimum of 40% in each of those to pass overall. Alright? The practical investigation lab report is worth 20%, and the examination paper is worth 50%, 30%, sorry. Alright? So, what I'm going to do, now, to start with, you probably aren't, if you've done BTEC, that's similar, you're likely to have covered this before, but then as we move on, there'll be differences in the depth we cover things to. Okay, so we're going to look at the main electrical quantities first up today. Voltage. Voltage is the pressure applied to the circuit. You can think of it as a force that pushes the electrons around the circuit, like pressure in a fluid circuit. Voltage is equivalent to the pressure. Yep. So we need, it pushes the current around the circuit, designated by the symbol V, and measured in the units volts, symbol V. Now, technically, in a circuit, we would normally use the symbol E for a source, like a battery or a generator. Yeah. After electromotive force, which is the proper technical term for the pressure. And then we would also be talking, if that causes current to flow in that direction, we'd have volt drops across components in the circuit. Voltage differences, potential differences across the circuit. One thing I will always pull you up on is if I hear you say there's 10 volts going through that resistor. No, there isn't. Current goes through, volts is across, or difference in pressure between 2 points. Yep. And we must have a difference in pressure for current to flow. If we connect both ends of our resistor to 12 volts, no current will flow. We need one connected to 12, one connected for current to flow from one high potential to low. Alright? The key point is that current flows in a circuit or component because of difference in the applied voltage at either end of the circuit or component. No difference, no current flow. Yeah. Current. The term current is a measure of the rate at which charge is flowing in a circuit, and designated by the symbol I, measured in amperes. No amperages, amperes. Amps up, we put the current up. Alright, we're electrical engineers, we use the right terminology. Okay, so current is a flow of electrons. So you can actually, you can encourage electrons to jump from atom to atom, and that's the flow of those electrons that is current flow. Okay. Resistance. Resistance in electrical circuit is the measure of opposition or restriction to current flow. So the resistance is what limits current flow. It's designated by the symbol R and it's measured in ohms. I'll qualify that, it's R for DC circuits. When we move over to AC circuits, we'll need to start talking about impedance Z, and that will become clearer then. Okay. When current flows through a resistance in its most basic form, electrical energy is converted to some other form of energy, such as heat, light, or the rotation of a motor. So without any resistance in the circuit, we haven't got a load, we're not going to do any useful work. So that resistor would heat up. If that was a lamp, that would light. If that was a motor, it will turn, because current's flowing through it. All parts of a real circuit have some resistance to flow, and without it, as you see, a house, pay for that. But every electric run back, it does some useful work in the meantime, mind you. I need to make it do that, and that's why. So, the main relationship between those three quantities and between the resistance of a circuit that flows in it. We use the symbol E instead of V where source F are being considered. You'll find that textbooks, some of them stick to E, some of them switch between E and V. If you've got equipment made in Germany, you as well. So I can really apologise for the confusion. We can rearrange them into three forms. A is equal to the voltage divided by the resistance. Equal to the current times the resistance, and R is equal to the voltage divided by the resistance. Could be 2. Yeah. We don't normally set a current, we make the current we want by adjusting the voltage or the resistance. So as understanding ordinary this underlying theory is more resistance, less current, a given voltage, less resistance, more current. If you remember that kind of underlying relationship, you'll never forget Ohm's law. Yeah. It's applied in many principles of electrical engineering, and you'll need to remember it. That will not be in any formula sheet, any exam that you take on this course. Staple understanding of electrical engineering, Ohm's law. And most of the stuff we do at level 6 calculation still comes down to Ohm's law. Still proves that every time. Ain't going to change. Alright. The other main electrical quantity we'll need to be considering is power. Power is the measure of the rate at which energy, measured in joules, is used. So 1 watt is when you're using 1 joule per second. In electrical terms, it's the rate at which electrical energy is converted into some other form. Power has the symbol P and is measured in watts. Power dissipated in a component or circuit resistance can be found using the following formula. P is equal to I times V. Okay? And there are two other key formulae for power. One is that you can get power from I squared times R, or alternatively from V squared over R. You need to commit those three to your general knowledge as well. Alright, they also will not be included in any formula sheet. So depending on which choose the one of these three thing here. Okay. There is a way, there are other ways one calculation, find the unknown, and then do a second calculation. But in a way, you're better off picking correct and the professional way to do it. And that's you use if you can. Okay? What's that note down there? It's not. It is most important to do the units after any result of any calculation in engineering. Otherwise, your answer is just any old number. Yep. So where units are appropriate, they must be included, and I do knock marks off in examinations if people leave units off. Also on this module, you should include the formula used and all your working, as this is likely to gain you some marks in the exam should you make a mistake with the calculation. So showing your working, you're going to get marks for the bits up to where you went wrong. Okay. The other thing is if a wrong answer is carried forward and you do everything else right with the wrong answer, that gives me a lot of work because I have to get the calculator out when I'm marking it, but you can't be penalised twice for the same mistake. So you'll lose your marks for that bit, and then going on from that, if you use that wrong current in the next bit of the question and do it exactly right, you'll get the marks for it. Okay? Yep. We kind of touched on this already today, so I'm not going to lay too much, but we got units, submultiples and submultiples. Giga, 10 to the 9. Mega, 10 to the 6. Kilo, 10 to the 3, and so on. Milli, 10 to the minus 3. Micro, 10 to the minus 6. Nano, 10 to the minus 9. And pico, 10 to the minus 12. And sorry? Tera. Tera's after giga, isn't it? Yeah. Tend not to get into those kind of quantities on this course. Remembering which way nano and pico go round is just remember they're in alphabetical order. Alright? So again, I shan't labour on that too much because we've already been through that once today anyway. Right. Next bit. Hang on, let's just have a look. I've done a lot today. Let's see if we can get you doing something.